What we are getting into today deals with rate mechanisms, okay? These are very easy. However, you know, I know I gotta say however, it depends on who you talk to, okay? Right, and these are very simple. We're gonna actually be able to fly through these. Make sure you guys got your pens and papers because we're going to get into this lesson right now. Here's what we're working with today. The rate mechanisms, again, this is like easy peasy, okay? What you have, and these are basic problems. Notice anytime you see A and B, guys, these problems are there for you to see how to do them the regular way with like a basic format before we actually add real chemical formulas, okay? That's why you see A and B giving you C. Because when I actually turn A into a real element, then you'll know how to do it, all right? You'll know how to do it. So for number one, this is the overall reaction. A plus B gives you C. All right. The proposed mechanism is slow. So what they want to know is in this question, is this an elementary step? Well, here's the thing. The answer is yes. Yes. And why? Because there's only one reactant, okay? Reaction. So yes, the answer is yes, okay? Yes, because there's only one step. A one-step mechanism is an elementary step. So the answer is yes. Now, for the part that says write the rate law comes directly from the elementary step, okay? And what you're going to do, you're going to simply say, all right, well, and if you all were here this week when we talked about rate laws, it's equal to K, which is your rate constant, times your A and your B. Okay? That's how you would write out your rate law. Okay? That's it. That's it. You don't have any data in terms of numbers, but what you do have is the chemical reaction. So in this particular example, A and B collide in a slow step right here. Okay, that's it. Look, y'all, nothing more to that. So we ain't got to overthink this one. We just going to do what? Move on now to problem number 2. Okay, so as y'all see me do this, I want you all to think, that's all we got to do. Yeah, that's all we have to do. Okay, look at this next one right here. Notice again, this is just one reactant, one product. Again, identify the reaction order. Well, in this case right here, because it's just one thing, this reaction order is just 1. Okay? Since you only have one thing, it's just 1. In this case right here, the rate law is just equal to K times A. And why just A? Because that's all you have on the reactant side. That's it. So think, single reactant breaking apart gives you first order, okay? That's that. And again, I can't say that's it enough, okay? I can't say that enough. Problem number 3 is going from easy to intermediate. Okay, well, but y'all can handle this, right? Okay, again, look at the difference here, okay? Look at the difference. You've got A plus B going into C. Then that's what the overall reaction should be, right? The mechanism is A plus B, which goes to D and is slow. Then you've got D to C, which is fast. Now, in this case right here, the D's canceled out, okay? They technically canceled out, which is why you see the overall of A plus B going into C. Okay? The slow step controls the rate. All right? Remember that. The slow step controls the rate. The slow step involves A and B. Okay? And as you can see here, the D that was there formed in one step and it was used in another step called the intermediate. Okay? So the intermediate is D. Yes, thank you, period. That's right. Yes. Again, the rate law comes from the slow step. So always refer to the slow step for your rate law, okay? For your rate law. So in this case right here, the rate is going to equal to K times A times B. And remember, we don't care about the product side, which is at C. We don't care about the product side. You always refer to the slow step for your rate law because the slow step pretty much sets the pace. Okay? All right. Next question. Okay. Let's look at number 4 now. Look at the overall reaction, A to C. This is the overall reaction. Apparently, the B's went away, okay? Since the B's went away, this is how you get your overall reaction. Now, they want to know, what is the intermediate? The intermediate is the one thing that was canceled out. So the thing that was canceled out were the B's. So the B would be the intermediate. Identify the rate law. Remember, the rate law comes from the slow step. So you look at your slow step, and that's going to tell you what the rate law would be. So right here, your rate is going to be equal to what? K times the reactant of A. Since A only appears in the slow step, the rate depends only on A. Nothing more, y'all. Nothing more. And what is the overall order for this? 1. That is the overall order. 1. So think of it this way. If only one molecule controls the slow step, it controls the rate. Okay? It controls the rate. Take a look at problem number 5. In this next example here, you've got 2A plus B giving you C. Now, again, I could give you a real example there, and it's going to do the same thing. You know, if I replace these letters, with real compounds, which we'll do that in a minute, it is the same process. Okay? Now, the mechanisms is A plus B going to D, that's slow. But then you got A and D going to C, that's fast. Now, how do we do this? We're going to cancel out our D, right? Now, when you add those two together, let me show you. And this is kind of answering the question. When you add these reactants together right here, you see the 1A here and the 1A there. 2A plus B gives you C, which is this overall reaction. So what is the intermediate? The thing that was canceled out, that D. So the intermediate here is the D. How do you write the rate law? You look at the slow step. The slow step is the first one, where it says A plus B goes to D. So the rate is going to equal to K times A times B. You never worry about the product side. You never worry about that D or whatever's on the right side. You only concern about the left side. Okay, so this is your rate law right there. That's your rate law. Okay, and then letter C. It says explain why the coefficient 2 does or does not appear in the rate law. All right, who can tell me why we do not use the coefficient of 2? Why do we not consider 2? And no, it's not second order. Why don't we use the number 2? I want y'all to think about what we're saying here. We never use coefficients. Hint, hint. Coefficients in the overall equation do not determine the rate law. Okay? Furthermore, you do not use coefficients at all when you're looking at your rate law. Coefficients are there just to look pretty. Kind of like the trophy wife. You're just there. Okay? You're just there. Or like what Marshawn Lynch said a few years ago. I'm just here so I don't get fined. Okay? So the coefficients are not used as a part of the rate law. Okay? You don't use that. Rate laws, they are only based on following those steps, not coefficients. So let's look at another example. Okay, problem number 6. Okay, problem number 6. And I hope that this is making sense to y'all, so that you can do this on your test with confidence. Okay? See, so far, I don't think y'all would get these wrong. Okay? I don't think you would get these wrong. All right, so take a look. The overall reaction is 2A goes to B. We know that the C's are going to cancel out. That's where the 2A comes from, okay? When we cancel those out, look at what's left over, okay? Your overall reaction is going to be the 2A that goes to B. That's what you have right there. The intermediate, can y'all tell me in the comment box, what's the intermediate? Good job, period. That's right. It is C. C is the intermediate. Okay, let's write the rate law. Again, the rate law is going to be based on looking at the slow step. Rate law is equal to what? Let me see if y'all can tell me the answer before I write it. What's the rate law going to be equal to? And you all can put it in the comment box. If you got this, you are correct. All right, very good, very good, very good. Okay. All right. Now, what is the overall order? Since you have just one reactant, it's 1. That is the overall order, okay? Since you have just one reactant, that is the overall order. So put your answer in the comment box. Okay, a reaction has the experimental rate law. Rate equals K times the reactant of A. Which of the following mechanisms is the most consistent with the data? The correct answer is B. And here's why. Because you only have one reactant, okay? You only have one reactant, that's why you have your rate law equivalent to just the A. If you put A and B for letter C, that means you would have to have A and B. So that's why letter C is wrong. And then letter D is also wrong because remember, the fast step cannot control the rate law. The rate law is based on slow steps. So you could have chosen between A, B, and C because letter D says fast step. Okay? Remember, although letter B also has fast step in part of the answer, if you look at the fact that it started off slow, then fast, that's why. And again, remember, A and B would mean that your rate law would have to look like this, but it does not. So we're going to cross that one out. Okay, we're going to cross that one out. So then when you look at letter A and B, well, again, you have two reactants here for letter A. So that's why that one is incorrect. So the answer is B, okay? The reason why it's not A is because, let me unhighlight A so that way you can see it, okay? The reason why it's not A is because if you look at A would be second order, and that's not the rate law for second order. So if you know your orders also in terms of identifying based on the formula, that also serves as a clue. If you look at what you're working with here for letter A represents a second order, and there are also two reactants here. And if you have two reactants, you would need to reflect similar to what you see in letter C. All right, so that's why the formula here would have to have two A's there. Even though those two A's could be something different, you would have to have two A's in the formula just like that. That's why. Okay, I'm going to give you a real example that you could use. And it's going to take me a minute to write all this out, so hold tight. I'm going to write it out because it's a long one. Well, you'll see what I mean. I just got to write it out. And I want you to show, I want you to produce the rate law, okay, that's consistent with this data that I'm getting ready to provide you with. So this is step 1. You've got NO. Okay, I'm going to zoom out so y'all can see the whole thing. This is fast right here, equilibrium. Okay, so that says fast equilibrium. I'm trying to write small, because of the width of my screen. Then in step 2, you've got N2O2 plus Br2, and it goes to 2NOBr, and then this is slow. Okay, what I want you to do in this example here is I want you to produce the rate law that's consistent with this experiment here. Based on what you see, give me the rate law. Okay, give me the rate law. Yes, you go to the slow step. That's right. Go to the slow step. For the rate law, if I ask you to give me the rate law, you would look at the second step right here, okay? You look at the second step because the second step is slow. Remember, the slow step produces or provides the rate law. So in this case right here, you're going to say rate equals K, and then in brackets, N2O2, close those brackets, and then Br2. That is your overall rate, your rate law. If I told you to give me provide the overall mechanism. How would you do that? What would you do? To provide me, I want you to provide me with the overall mechanism. What would you do? You would have to go back in and start canceling things, okay, that you no longer need. So I'm going to get rid of the N2O2 with the N2O2 here. That's right. Cancel the intermediates. Exactly. Cancel the intermediates. And the intermediates, if I say identify the intermediate, you would tell me it's N2O2. Okay? N2O2. Whoops. And now, the overall reaction in this case, based on what you see here, would be, remember, you have two NOs at the top, right? There are two NOs at the top. So you're going to say 2NO, okay, plus Br2 gives you 2NOBr. And just like that, you're done, okay? You are done. So we're going to do another one just to make sure. Okay, here is step 1. Letter A. I want you to determine the rate law. And letter B, I want you to give me the overall mechanism, okay? And identify the intermediate. Okay? Identify the intermediates. And I put an S there because there may be more than one. Okay, so here it is again. Step 1, step 2. Letter A, determine the rate law. Letter B, give the overall mechanism and identify the intermediate. For letter A, you go by the slow step, okay? For letter A, you go by the slow step. So the rate for this one, in this particular case right here, is K times NO2. I'm trying to write A because that's what we've been talking about all along. But it's NO2, just like that, okay? But in this particular case right here, you're going to put the 2 there because there are 2 of them, okay? Because there are 2 of them. And what you have to also recognize, okay, is that the rate law is based on step 1, and this is a biomolecular process, okay? This is a biomolecular process. So in some of your reactions, if you have just a single molecule, those are unimolecular. In this case, when you have 2 reactants, those are bimolecular, okay? And then if you have elementary steps that have like 3 molecules, those are teramolecular, all right? So those are some examples of some of the things that you will see in your chemistry. Now, what I'm going to do here, I'm going to give the overall mechanism. So for part B, what I'm going to have to do, I'm going to actually put this in a different color. Yes, because you have 2 of them here, that's why. That's where that 2 comes from right there. Yep, because you have two of them. Now, I'm going to put this in a different color for part B now, okay? So for part B, because I got to start canceling things out. Remember, when you do the overall mechanism, you have to cancel what's called the intermediates. The intermediates are those that appear on both sides of your reactions, of your steps. This is similar to like Hess's law when you all took when you all took Chem 1 and you dealt with Hess law, you had to cancel things that are the same on both sides. Even in spectator ions, you hear that word when you talk about oxidation and reduction. So I've canceled out my NO3s because they're on both sides of the reaction here. Okay. So we got rid of those. Then we're going to get rid of the NO2 also because they're on both sides as well. So your intermediates here are those that were canceled out, okay? So your intermediates are the NO2s and the NO3, okay? Those are your intermediates. Now, your overall reaction, okay? Your overall reaction is going to be what's left over, okay? What do you have left over? What do you have left over? So I drew a red line so that you all know that I'm going to write that out right here underneath for part C. I have NO2 plus CO, leaving us with NO plus CO2. That is your overall reaction. And just like that, it's it. That's it. And you all notice I color code stuff because you're welcome, honey. You're welcome. You'll notice that I color code things because I want you all to see where you get your answers from. I color coded pink for slow because that's how you determine your rate law. I color coded that teal blue because that's where the intermediates were. And then I drew a line for red to say, well, what's left over? That's your overall mechanism, rate mechanism. Okay? What I want you guys to know is that chemistry does not have to be intimidating if you just practice, practice, practice. If you are a singer, a dancer, whatever extracurricular things that you like to do, you have to practice. You just can't do it one time. You have to practice over and over and over until you become better. That's the same thing with chemistry. And as I've said before, you have a great day as well, Safa. As I've said before, if you practice at least 9 hours a week of your chemistry, this will be easier for you to understand.